Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 1 of our unit Magnetism and Matter. Let's begin with today's class. In this session we will be having an introductory session of the magnetism and how the magnetism has arrived, what would be the history of magnetism and the basic definitions and basic elements of magnet which we should be known. So let's begin then. The word the word magnet is derived from the name of an island in Greece called Magnesia, where magnetic ore deposits were found in 600 BC. And their shepherds were there on this island complained that the wooden shoes, which had nails at times, stayed stuck to certain grounds. Even their iron-tipped roads were similarly affected, and this attractive property of magnet made it difficult for them to move around. So this was initially they have a problem, and even Chinese texts dating 400 before century mention that the use of magnetic needle for navigations on ships. So they have used the magnetism even on that time. The property, we can say the property of a magnet to attract iron was discovered in a rock that found in the ancient mineral rich region of Magnesia, and this rock was known as the lodestone. It is an example of natural magnet, and the name magnet is derived from the iron ore that we call as a magnetite Fe3O4. It was found near the ancient cities of the Magnesia, and Fe3O4 contains about 72% of the iron, and it is heavy and dark gray to black in color. We understood that we have played with a magnet at some point of time in our childhood, and we have seen that magnet always attracts the iron nails or the pins. This graphic represents that magnet is attracting an iron nail. So basically there are two basic properties that has been observed in the lodestone. One is the attractive property and another one is the directive property. Now what attractive property is, when a piece of lodestone is brought near the iron fillings, they cling to the lodestone. So this you can see in this diagram. These are the iron fillings that has been cling to the lodestone. And in the directive property, when a piece of lodestone is suspended freely, it comes to rest in the north south direction. So why north south direction? Let's see. The earth, we can say the earth behaves as a magnet, and its magnetic field of the earth points from the geographical south to the geographical north. This is the magnetism of earth, which we call as an earth's magnetism. Now let's look at the bar magnet. Yes, very famous, and we have even studied it at our classes, maybe class 6, maybe class 7, maybe class 8, at various part of our curriculum. So bar magnet, we can say a bar magnet is a rectangular solid magnet which attracts other magnets or iron or that substance that containing iron. Yes, it look like this. This is the bar magnet. And when we say it's the poles of a bar magnet, that is the pole pointing to the north was termed as the north pole. This is the north pole of the magnet, and the pole that pointing to the south was termed to as the south pole of the magnet. Now when a bar magnet, let's suppose one of the magnet is there and it has been cut from here. So when a bar magnet is cut vertically, each piece also acts as a magnetic dipole. So this is the situation. I know this all are the information that we have studied in our early years. Yes, so even though this has been revised so that things can be brushed up. So if it will behave as a two magnets, something like this, it's a north south, it's a north south. Again this has been divided in two segments, it's a north south. If again they have been cut it out, it's a north and south, something like this. And when we cut it, we must understand that it is not the possible that only north pole would be there and on the other magnet south pole would be there. No, this is not possible because m- in the magnet, monopoles does not have any existence. That means we cannot say that this is the north pole of a magnet. No. When north pole would be there, south pole must be there. So monopole doesn't exist in the magnets. I hope this is clear. This is the basic difference. This is the basic difference between magnetism and electrostates. In electrostates, a single charge do exist. It is possible that only positive charge is there, or it is possible that only negative charge is there. But in magnet it is not possible. But magnet it is not possible that only north pole is there, only south pole is there, and so on. So let's look at certain questions. It's a chemical formula. Chemical formula of magnetite. It's an Fe3O4. Yes, it's a formula of magnetite. Next, it contains magnetite contain about blank of the iron. How many percentage? It's yes, it's a 72 percentage of iron it contains. Next question. The earth behaves as a magnet with the magnetic field pointing approximately from the geographically from where to where. Let's say this is news. That means this is north, this is east, this is west, this is south. So from south to north it will pointing out. Next, magnet exists in the form of always in the form of dipole, not exist in monopole or tripole. Yes. So these are the very basic questions, basic information that we already know. We just have a certain brush up kind of things so that things would be re clear. Yes. So now let's discuss certain basic terms that are related to magnet. Let's begin then. That we have this a bar magnet. This is the south pole, this is the north pole. Let's first start with the pole. What we can say pole about pole is that it is the two regions near the ends of a magnet where the strength of a magnet is concentrated nearby the poles. So magnetic field or magnetic capability is maximum near the poles. North pole and south pole. What is north pole? It's a end of freely suspended magnet pointing towards the geographical north. And south pole, it is the end of freely suspended magnet that pointing towards the geographical south. So this is north pole, this is the south pole. Now let's look at the pole strength. Pole strength that has been denoted as small m. It is the concentration of strength of a magnetism at the poles of a magnet that we can call as a pole strength. For n pole this is considered as conventionally this is plus m, and for the south pole this is concentrated, this is assumed as minus m. So such as when we say proton, when we say proton, we say it's a positive charge. Why positive? Then we say conventionally we have defined it that proton would be having a charge of positive, and when we say electron, then it would be having a charge of negative. Why negative? Then we will say that no, that we have decided, that we have conventionally decided that proton would be having a positive charge only, and the negative charge will be given to the electron. So again these are the same thing. For the n pole, for the north pole, we have decided that it would be having a positive pole strength, and for the south pole it is having a negative pole strength. And this pole strength, it is a scalar quantity. SI unit, ampere into meter. How we can derive it, we will see it later on, but at this point of time just remember it, that SI unit of pole strength, it's an ampere into meter. Does it clear? Yes. I know these are the all the theoretical things. Yes, this is the unit which contains many theoretical aspects, and so many theories were there. But but this is very important unit when we talk about the NEET examination specifically, because certain segments have been removed from the JE sections. But in NEET examination, still everything is there. So we are going to cover each and everything. So let's look at the magnetic length. Magnetic length. We can say the distance 2L between north and south pole is called as the magnetic length. This is our north, this is our south pole, this is our north pole, and the distance between these two poles, distance between these two poles is the north. It's called as the magnetic length. I hope this is clear. Is it clear? Yes. And it is a vector quantity, it is a vector quantity, and it always directs from the south pole, from the south pole to the north pole of a magnet. SI unit, obviously it is a length, so SI unit would be the meter. Now one more term we can define, it's a geometrical length. One more term that can be defined as a geometrical. When and when I say geometrical length, the geometrical length will be simply the, it is the length that can be measured using a scale for any magnet. So if any magnet is there, if any magnet is there, and if I want to measure its length, or I should say, if I take a scale and measure it, it will be the geometrical length. I hope this is clear. And always here magnetic length is equals to 5 by 6 times of the geometrical length. 5 by 6, that is approximately from 85 to 91, because certain authors have written it that it is 85 percentage, certain authors written it's a 91. Yes, certain author just write it's a 9 by 11. Yes, no, it's a 9 by 10, sorry, 90 percentage. So different author to author the things have been varied, but it is approximate. But we must be sure for this, that magnetic length is less than geometrical length. And now, very important, next is the magnetic dipole. Yes, magnetic dipole, it is a pair of equal and opposite magnetic poles. North pole of pole strength plus m, north pole of pole strength plus m, and south pole of pole strength minus m, separated by finite distance to L. This is the same thing when we used to discuss, about the electric dipole. Yes, in the electric dipole we have two charges, one is positive, another is negative, and they have been separated by a certain distance, let's say L or 12 something. Even here it is the same thing, magnetic dipole, it is the same thing, it's a pair of equal and opposite magnetic poles. North poles having pole strength of plus m, and south pole having a pole strength of minus m. Here it is separated by distance 2L. Yes, we can say magnetic dipole. Yes, we must understand that it is a vector quantity. It is a vector quantity. I hope this is clear. And as the electric dipole was there, let's draw it here. It's a minus q, it's a plus q, and and the direction of electric dipole is from negative charge to the positive charge. We denote it by p. So even here the direction of magnetic dipole is from here to here, and that has been derived by m. It is from the south pole, that is having minus pole strength, to the north pole having positive pole strength. Value of the dipole, that could be written as m is equals to any one pole, I mean any one monopole, multiplied by distance between these two poles. Here distance between two poles, it's a 12, it's a m into 12. I hope this is clear. So from this we have derived the unit of the pole strength, small m. Yes, it's m is equals to capital M divided by L. This m was the ampere into meter square, divided by length, it's a meter. So this is, thus we have derived the unit of pole strength, which is ampere into meter. Does it clear? Does it? Are you sure? Great. Now, axial and equator. When I say axial or axis, it is an imaginary straight line that passing through the two fictitious poles of a dipole, that we call as an axis of the dipole. When we pass an imaginary straight line passing through the two poles of a dipole, that we call as an axis of the dipole. And let's look at the equator. It is an imaginary straight line passing through the center of the magnetic dipole, and which is perpendicular to the axis that is called as the equator of the dipole. So it's an perpendicular to the axis that we call as the equator of the dipole. Does it clear? Does it? Yes. Great. Now, as we have Coulomb's inverse square law for the electrostatic, same way I am having an Coulomb's inverse square law for magnetism as well. Yes. So when we say two monopoles are there, two isolated magnetic poles are there, let's suppose one of them is m1, another is the m2. The distance between these two monopoles are the d. This is just the hypothetical concept that monopoles do exist, because we want to compare this with the electrostates, and in electrostates mono charge do exist, as we have discussed previously as well, that in electrostatic positive charge alone can exist, negative charge can alone can exist, but monopole does not exist. Yes. Even though we are talking about it as in hypothetically, so please understood the assessment that we understand that monopole does not exist at all, even though even though we have been derived a certain theories that uses only the monopoles. Yes, this is what hypothetical analysis is all about. So a force between two isolated and magnetic poles that can be represented as F is equals to mu by 4 pi multiplied by m1 into m2 divided by d square. It is the same system, same. It's mu naught by 4 pi into m1 into m2 d square, such as it's a k q1 q2 by r square. Yes. So in here, it's a mu is the absolute permeability of the medium between the poles. And when we say this, that these two monopoles have been placed in air or vacuum, when these two monopoles have been placed in air or vacuum, this F could be written as F is equals to mu naught by 4 pi into m1 into m2 divided by d square, where mu naught is the permeability of free space, and the relative permeability can be written as mu r is equals to mu by mu naught, or we can say mu is equals to mu naught into mu r. Does it clear? Does it? Any doubts, any concern over it this? Do you have any concern, any doubts? No? Everything is clear? Is it clear? Absolutely, completely? Are you sure? Great. So let's now again discuss certain things about the magnetic dipole moment that we denote as the M. So when we say magnetic dipole moment, we can say it's a magnitude of magnetic dipole moment is defined as the product of magnetic length. Let's suppose this is the magnetic length. It is always the shortest path, or we can say shortest distance between two monopoles that we call as the magnetic length. So it is the product of the magnetic length and pole strength M, that could be written as M is equals to M into 12. We can know, and we must understand that it is a vector quantity. Even we have used it in the previous unit, moving charge and magnetism. So it's a vector quantity which is directed from the south pole to the north pole. Is it clear? Is it? Yes. Its unit has been derived from here. It's a m is equals to I into a. It's an I stands for ampere, and a stands for area. For area, we have written it as a meter square, so it's an ampere into meter square. I hope this is clear. Is it clear? We must understand that it is a vector quantity. This is vector quantity. I hope this is clear. Is it clear? Do you understand each and everything up till now? Up till now, is it clear? Are you sure? Are you? Great. So now let's find out The question is find out magnetic moment, or I should say magnetic dipole moment for the given situations. Let's suppose one bar magnet has been kept over here. It's a north pole, it's a south pole, and let's denote it as an N1 S1, and this is N2 S2. So what I need to find out, I need to find out magnetic dipole moment for the given situations. So let's begin. First, it's an N1 S1 and this is N2 S2, as they have been given a separate numbers. They have given an individual number. That means they are not the identical magnet. If NS has been written, that means we can understood that they are the identical magnet. Now, direction of magnetic moment of first magnet is in the negative x direction. This could be written as M1 from south to north. For this, it is again from south to north. This is M2. So while I say M net, I must write it would be an M1 plus M2, and this total would be in negative I cap. Does it clear? Does it? Great. Ready for the next? Yes, it is just the practice of vector. Yes, but we must do it because this has been asked. This has been asked. We will see it later on. It's an N1. It's a S1. This is S1. This is N1. So this could be written as S2 N2. Sorry. So S1 N1, it is in this direction. It is in this direction from negative pole, negative monopole to the positive monopole. This is M1, and for this it is on here. Both are having an opposite direction, and when they are having an opposite direction, we can say it's an M net that could be written as M1 minus M2. Does it clear? Does it? Great. Let's look at this. That this is the situation. Let's suppose this is NS, even this is S and N. When I say, when I have not written any number, it is just NS. Yes, that means they are the identical dipoles. They are the identical dipoles, and that can be solved easily. So this is this for them. For it's a first, it's a S to N. This is first, and for this it's a second, it's an M2. So this is, as this two are the equal, M net should be equals to root of M square plus M square. That could be written, as root of 2M. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now let's suppose something like this. It's a north, this is south. This all are the identical dipoles. This is north, this is south, and this is south, this is north. So for this, this is for south to north. This is magnetic dipole M, moment M. This is magnetic dipole moment M. This is south to north, this is in this direction M. This is in south to north, this is in this direction. So in totality, if I add this two, because this both are in the same direction, MM, this could be written as 2M. This is M, this is M, this could be written as again 2M. And this M net, would be equals to root 2 times of 2M. Is it clear? Is it? Are you sure? One more. Let's have a look. Suppose they have given something like this. This is south, this is north. This is, let's say south, this is north, and this angle is theta. So one of the magnetic dipole moment is in this direction, this is M. Another magnetic dipole moment is in this direction, this is M. and these two vectors are there, both are having same magnitude. This is m, this is m, and they have been angle theta. So when they are having an angle theta, what I can have is it's an m dash that should be is equals to 2m sine theta by 2. This is m dash. So this could be written m dash is equals to 2m sine theta by 2. I hope this is clear. Is it? Is it clear? Great. Let's look at the next question. Keep it continue. You are doing good thing. Very good. One. This is south. This is north. Second. This is south. This is north. And the third. Let's assume that they are making an equilateral triangle. They are making an equilateral triangle. This is south north. So find out the net magnetic moment of the given figure. So what I supposed to do is that this is south, this is north, this is the magnetic moment 1. This is the magnetic moment, sorry, this is the magnetic moment of 2. This is m, and this is the magnetic moment of third one. So this given diagram can be represented as that this is something like this. Yes, this is something like this, and this has been something like this. I hope this is clear. Is it? So what I can do is this is 60 degree, this is m, this is m. Yes, and angle between this two is the 120 degree. So first let's just solve this m. So that could be written as first this 2 m resultant 1 is equals to 2 into m into sine of theta by 2. Sorry, it's a cos theta by 2. Sorry, my mistake. It's an m dash is equals to 2m. Even I made a mistake over here. Sorry. It's an m dash is equals to 2m cos theta by 2. So even this would be m dash cos theta by 2. So this is equals to 2 multiplied by m into cos 60 by 2, which would be a cos of 30 degree. While I say cos 30 degree, it's a 2 into m into cos 30, which is root 3 by 2. It's a root 3m, and the resultant would be in this direction. So while I say so that the resultant would be in this direction, now I am having this 2, this and this. Yes, well, this was the 90 degree, this was the 120 degree, this was the 30 degree. This would be the angle theta. Now you can do this. This is m, this is root 3m, and remaining according to the vectors relations, m1 square plus m2 square plus 2m1 m2 cos theta. You can do this, the rest of the thing. Is it clear? Is it? So can you do this? Basically this is only the vector practice using which you are going to calculate the mnet. Are you clear with this? Are you are you clear? Great. So this is the first kind of question. Where you have been asked to do the mnet. So can you do this? Can you do this? Are you sure? Okay, next the next situation is when we have been asked to find out the magnetic moment in certain situation, that is something like this, that this is one of the magnet where this is south pole, this is north pole, and and the length is given as 2L. In this situation another magnet has been there, and this is north pole, this is south pole, again this is 2L. Yes, and we have been asked to find out the magnetic moment. That could be written as m for here, and this is south to north, so m for here. So it is something like this, that for first it's something like this, for another it is over here. So this m net would be root of 2 into m, and in certain options m were not there. So what you need to do is you need to replace this with this m and this l. So in this situation this could be written as root 2 into m into 2l. Yes, or I could write it as a 2 root 2 m into l, ampere into meter square. This is the unit. I hope this is clear. Is it clear? Is it? So can we do this? Can we? Can we do this? Are you sure? Are you? Are you sure? Great. Now let's suppose the situation is that when a bar magnet is cut into n equal parts, which is parallel to its axis. This is the axis of the magnet, and we have divided this magnet into n equal parts parallel to its axis. So what happen is that if you look at this pole strength, you can look at this pole strength has been divided into separate parts, and it has been divided by m segments. So we can say pole strength of each part, pole strength of each part, this m dash could be written as m by n, and the length of the each part, let's suppose this is the length l. So length of each part will remain the same. So as length of each part will remain the same, it would be a 2l dash, that would be equals to 2l. So when I calculate the magnetic moment, my initial magnetic moment was m into 2l. Now my m would be replaced by m by n. 2l will remain the same. So this magnetic moment of each part can be represented as m divided by n. It is the magnetic momentum of each part. I hope this is clear. Is it clear? Great. Now let's suppose we are doing the next thing, which is a bar magnet. Bar magnet is cut into n equal parts, but now at this time normal to its axis. So this is the south pole, this is the north pole, and we have divided this magnet, we have divided this segment into n equal parts along its axis, that is the perpendicular to its axis, sorry. So now in this time is, if you look at this, the pole strength remain as it is, but now the length has been divided into n parts. So pole strength remain as it is, this is m dash, that would be equals to m, but the total length is going to be divided, and that would be said as the 2l by n. So now the magnetic moment of each part, would be represented as m dash is equals to m by n. Is it clear? Is it? Are you sure? Now let me do one more thing, that let's suppose this is our bar magnet. This was the initially bar magnet. Let's suppose this is the south pole, this was the north pole, and this was the length, it's 2l. Now suppose we are dividing this into x equal parts, and now in this direction, let me use one more color, that yes, in y equal segments. So initially m was pole strength m multiplied by length between two poles, this was 2l. Now in this new situation, for the m dash, it would be an m dash multiplied by 2l dash. While calculating m dash, what I understood is that pole strength has been divided into x parts. So m dash is equals to initial m divided by x, and this length has been divided into the y parts. So this is 2l dash, that should be is equals to 2l by y. So this m dash can be written as this is m by x multiplied by 2l by y. So this would be 2 into ml divided by x into y. So this 2 into ml or m into 2l is the original m. Yes, before it has been cut down. So this is m divided by xy. I hope this is clear. Is it clear? Is it? Are you sure? So can we do this? Can we? Can we do this kind of things? Are you sure? Are you? Can we? Are you sure? Let's have a look. That suppose I have given that this bar magnet is there. This is plus m. Sorry. This is plus m. This is minus m. This length is 2l. This length is 2l, and it has been divided. It has been divided into two segments. So magnetic moment of any one of the piece is, if let's suppose this is m, which is equals to m into 2l, then this would be m dash is equals to you can see length has been divided. This is plus m, this is minus m. So this would be equals to m into l, because this is only the l length would be there. So this would be capital M divided by 2. A same situation can occur over here, something like this, that it has been divided into two parts, or I should say it has been divided into two equal parts. The initial m was m into 2l. This was the 2l. Now if I understood any one of the part, it's an m by 2 multiplied by 2l. So that could be written as m into l, which is m dash is equals to m by 2. I hope this is clear. Was it clear? Was it clear? Are you sure? Are you? Great. Now let's suppose one more. Yes, it has been divided like this. So any one of the segment, let's say I'm talking about this segment only, that could be written as m dash is equals to original m divided by 4. That's it. Yes, it's an m divided by xy. It is as simple as that. So can we do this? Can we? Is it possible for us to do this? Are you sure? Are you sure? Can we do this? Great. So now let's look some more cases. That this is the case when a thin bar magnet of magnetic moment m and length 2l is bent at its midpoint with an angle of theta between the two parts, then its new magnetic moment. So first what you need to observe is that this is the south pole, this is the north pole, so this magnetic moment would be in this direction. This is the south pole, this is the north pole, so this magnetic moment would be in this direction. So it is something like this, and this angle would not be the theta, but this is 180 minus theta. Yes. So when I write this, let's say this is m1, and let's say this is m2. When I write this m net, that should be equals to root of m1 square plus m2 square plus 2 m1 m2 cos 180 minus of theta. And this cos 180 minus theta, could be written as it's an m1 square plus m2 square minus 2m1 m2 cos theta. As it is minus, it has been returned as 2m sine theta by 2. I hope this is clear. Is it clear? Is it? So please note it down that here south pole is here, north pole is there, and in this case south is here, north is there, because you have just bent it. You have just bent the bar magnet and design a new structure. I hope this is clear. Now next, whatever we are going to discuss, this is very interesting, and questions based on this has been asked in every alternate examinations. So let's suppose what it would be. It says that, let's suppose this is the bar magnet, this is plus m, this is minus m, and this length is 12. Now if this bar magnet, this, let's say this m could be written as small m into 12, it's a pole strength multiplied by length between two monopoles. So if a bar magnet of moment m is bent into an arc, so it has been bent to an arc, so that angle at the center of the arc is theta, then the new magnetic moment, a new magnetic moment could be written as m dash. That should be is equals to 2m sine theta by 2 divided by theta, where theta is in the radians. So is it clear? Is it is it clear? Are you sure? Have you noted down? Have you noted down? The magnetic momentum of this is the m dash, which I have derived. It's an m dash is equals to 2m sine theta by 2 divided by theta. Does it clear? Any doubts? Anything? Anything? Are you sure? Great. So let's have just practice of this. That the situation is something like this. This is plus m, minus m. This is 2l. So this is plus m, this is minus m, and this is 2l. And the magnetic dipole moment is from negative to positive. So this would be in this direction. It is in this direction. Now let's suppose this has been bent like this. It's a semicircle. Yes, something like this. Let's suppose this is south pole, this is north pole. So one of the option is m dash. That would be equals to 2m sine theta by 2 divided by theta. This is equals to 2 into m into sine theta. Yes, this theta is 180 degree. This theta is 180 degree. So this is 2m sine 180 by 2, it's a 90 degree, divided by theta. Theta could be written as pi. So sine 90, it's a 1. So this could be written as 2m by pi. This is one of the option. If you have remembered the formula and you know the everything about the formula, how to use it. Now let's suppose we have forgotten the formula. Let's suppose we have forget the formula. What could be done? So what we are supposed to do is that let's see the basic approach, that this is the, let's suppose, radius r, and the initial magnetic moment was m into 2l. That is the length of the two monopoles. Length between two monopoles is the 2l, and from this length 2l I have made this semicircle. So what I can write is, it's a 2l is equals to pi into r, because this is the just a semicircle, and as it is a semicircle, r could be replaced if required, would be in 2l by pi. Now what is m dash? What is m dash? We can write down, it's an m dash is equals to m multiplied by distance between two monopoles. While I calculate distance between two monopoles, it is the shortest path that I need to consider. And when I calculate the shortest path, that should be m dash is equals to m into 2r. So this could be written as m multiplied by 2, and r can be replaced. R could be replaced, it's a 2l by pi. So if I rearrange this, that could be written as 2 multiplied by m multiplied by 2l divided by pi. Now this m by 2l, it is the original magnetic momentum, or I should say magnetic moment of this horizontal section. So this could be written as m dash, that would be given as 2m by pi. Yes, so it is obvious that answer would be the same. that is very obvious thing. But this is the approach. This is the approach number two. Yes, that is the manual approach, that you need to convert it and you need to do everything for it. And the other approach, the other approach to do this is just the formula based approach. You can do one thing, that you can remember the formula when and when require you can apply it, because it is the faster approach. But even if you have forgotten the formula, because it happens certain times that we are just blank at a certain moment of time and we don't remember that what the formula was, and whether it would be a sine theta or whether it would be a cos theta and everything, then manual approach must be there. Manual approach must be there so that we can have an answer. May take some time, but at least we have an answer. I hope this is clear. Is it clear? Is it? Now any doubts, any issue over this? No? Okay, great. Let's have one more question based on this, that we have a bar magnet something like this. It's a plus m, this is minus m, this length is the 12, and let's suppose I have converted this magnet to this. It's a 1/4, and this is plus m, this is minus of m. Let's say this is r and this is r. So if this is the magnetic moment m, which could be written as m into 12, find out the magnetic moment m dash. So let's go with the formula approach, that could be written as m dash, that would be equals to, this m dash could be written as it is 2m into sine theta by 2 divided by theta. So this could be written as 2 into m into sine theta by 2. As you can see, it's a 90 degree. 90 by 2, it's a sine of 45 degree, divide by theta. Theta could be written as pi by 2. 180 by 2, 90. Yes. So this is m dash, this would be equals to 2 into m into sine 45. The sine 45 could be written as 1 by root 2 divided by pi by 2. It's a pi into 2. So this could be written as 2 into 2, 4. This is 2, this is root 2, so this is root 2. This is 2 root 2 multiplied by m divided by pi. This is m dash. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? This m dash, that should be is equals to 2 root 2 into m by pi. Does it clear? One more. Let's have a look. That, let's suppose a situation is something like this. Yes, this is plus m, this is minus m, this is length 12, and this has been bent to an arc. Let's suppose this is north, this is south, and if I extend this, this could be the 60 degree. So this m should be is equals to m into 12. They have asked that what m dash is. It's an m dash that could be equals to 2m into sine of theta by 2 divided by theta. So that could be written as it's a 2 into m into sine of theta by 2. It's a 60 by 2, which is a 30 degree, divide by 60. That could be written as pi by 3. So that is m dash, that should be is equals to 2 into m into sine 30, which is half, divided by pi by 3. So this 2 2 has given, and this is 3m by pi. This is m dash. I hope this is clear. Is it clear? Is it? Are you sure? Are you? So can you do this? Can you? Can you do this? Great. Let's move on and let's check certain more questions. It says that, let's suppose this is the one of the pole. This is one of the magnet, S1 N1 is there. Another magnet is there. This is S2, this is N2. So magnetic momentum 1, magnetic momentum 1, this would be M1, and magnetic momentum 2, this would be the M2, and the angle between this two, angle between this two is an angle theta. So if I calculate the m net, if I calculate the m net, that could be given as root of m1 square plus m2 square plus 2 m1 m2 cos theta. Yes, this is the same. R is equals to root of a square plus b square plus 2ab cos theta. Yes, it is the same thing. Got it? Are you sure? Are you? Great. Next, let's suppose the question is, or the case is, when two magnets of magnetic moments m1 and m2 are kept at touching each other with an angle theta, with like poles touching each other, then the resultant magnetic moment, when like poles are touching each other, then it could be written as, when the with like poles, or I should say, yes, when like poles touching each other, then this is the south pole, this is the north pole. Here it would be a south pole, this would be a north pole. Yes, this is not the like poles, these are the unlike poles. These are the unlike poles touching each other. Yes, so this is from south to north, this is the m1. Again, this is south to north, this would be the magnetic moment 2, and this is magnetic moment 1. So this is the angle that could be written as 180 minus theta, and this could be written as m dash, or the m net, that is equals to under root of m1 square plus m2 square plus 2 m1 m2 cos 180 minus theta. When I say cos 180 minus theta, it would be a minus. It would be a minus. It's an under root of m1 square plus m2 square minus 2 m1 m2 cos theta, and that's it. So have you done this? Yes. Can this be done? Yes, this is more or less a practice of on vectors only. Yes, that but we must make sure that this can happen with us. This can be done with us. I hope this is clear. This must be done from us. This is very simple. This is a very simple. Yes, and these are the units which are just like the units which are very easy to understand, first thing, and second thing, this all units have very limited applications. When if you begin with the moving charge and magnetism, and you will end it before ray optics, this all are the units which are have very limited applications. Even though they are having a limited applications, they are having a huge capacity of asking in the competitive examinations. Yes, so please have a look at this. Please have a look at this. Please take this theoretical sessions as well very seriously. Yes, please take this theoretical session as well very clearly. This will help us, yes, to score good numbers. So let's look at the certain MCQs. It says that for a magnet, the direction of magnetic dipole moment. Yes, it was something like this, that this was the bar magnet. This is the bar magnet, and this is the south pole, this is the north pole. By convention, we take a south pole as a plus m. Sorry, by convention we take south pole as a minus of m and north pole as a plus m, and the direction of magnetic dipole moment is from negative monopole to positive monopole, it is from south pole to north pole. Does it clear? Does it? Next, for a circular coil, magnetic dipole moment is given by, we have this relation that m is equals to I into a. But if this coil contains, if this coil contains n number of turns, if this coil contains n number of turns, then m can be given as n into I into a. This is equals to ni. Yes, this would be the correct answer. I hope this is clear. Is it clear? Does it? Are you sure? Great. Now let's look at the last question of this lecture. It's a magnetic length that would be equals to blank's geometrical length. Yes, it's a 5 by 6. I hope this is clear. So there are certain concerns, there are certain topics which are information point of view, they are important. So please learn them. Please learn them and go for them. Yes, because they want that kind of applications only, that you need to remember it. So let's just wind it up this session over here. This is all about the introduction to magnetism. From the next session we are going to start, from the next session we are going to discuss it, the magnetic field and their applications, their various applications as a point of view of the monopole and dipole and everything about the magnetic dipole moment and their magnetic field and all that stuff. So before you tune into that lecture, I request you guys to please revise this very carefully, because from the next time we are going to use the same concept that we have used today, that south pole is considered as the negative monopole and the north pole is considered as a positive monopole. One more thing I want to clarify it, that from the next session we are going to discuss about the magnetic fields due to monopoles, due to dipoles, that means on the axial point, on the equatorial position and all that stuff. So I request you guys to revise electric charge and field, because all the cases that we have discussed with electric charges, all that cases we are going to discuss it again and again, but in a very shorter way. So please revise that before you tune in to the next session. This will help us to cover a lot of syllabus very quickly, even though effectively. I hope this is clear. Is it? So please revise this. Please have a practice of the mnet. Yes, that is the net magnetic dipole moment. Once you practice it, that will deliver to the subconscious mind, and this will help us to get it done anytime, when I want. I hope this is clear. Yes, thank you. Have a good day. Take care. Bye bye.